In this section of chapter 16, we will discuss uh, different definitions of strong acids, weak acids, strong bases, and weak bases. First, I'll begin with Arrhenius' definition. Arrhenius' definition is defined for solution in water. So in water solution, an acid gives off H plus ion. So basically they must have hydrogen, and not only that, it must break down to give off H plus. So HCl, for example, that breaks down into H plus and Cl minus. So it's an acid. Same is the case with H2SO4 that breaks down into H plus and HSO4 minus. Here I should also mention about a strong acid as well as weak acid. A strong acid would break down 100%. For example, HCl is a strong acid that would break down 100%. If I have, for example, 0.1 moles per liter of HCl, all that 0.1 mole would break down into H plus and Cl minus. So there'll be no HCl be left as H form, as HCl form. So at the end it'd be 0 here, but it'd be 0.1 here and 0.1 here. So there'd be 100% breakdown. And that's the case with all strong acids. Weak acids, mostly organic acids, only part of those would break down. Say out of 100, maybe 1, 2 of them would break down. On the other hand, for a strong acid, if I have 2 molecules HCl, all those 2 molecules would break down. Similarly, I can define a base. Base is the substance that gives OH minus in water solution. And these are all strong bases that we're looking at now that I have highlighted in red. Calcium hydroxide, sodium hydroxide, magnesium hydroxide is mostly group 1A. If you look at periodic table, you'd find that these metals appear in group 1A and 2A. So group 1A and 2A hydroxides. So group 1A and 2A hydroxides are strong, would give strong bases. So what does that mean? Again, 100% ionization. If I have calcium hydroxide, I'm going to show you what happens. If I have calcium hydroxide, it would 100% break down into calcium 2 plus 2 OH minus. So there'd be nothing left over as CaOH2. All of them would break down in water, giving 2 OH minus per molecule of calcium hydroxide. And that's why it's a strong base. Now, Bronsted-Lowry definition is the second type of definition. It's defined as an acid is a substance that gives off H plus in any solution, not just water solution. A base is a substance that accepts H plus in any solution. So it's not confined to just water solution. So it broadens the definition of acid and base. Here we're looking at one reaction of ammonia and H2O. This is a well-known reaction which gives NH4 plus and OH minus. So water basically breaks down as H plus and OH minus. H plus gets bonded to NH3, and that's how you get NH4 plus. Now, NH3 is a well-known base. It takes up H plus from water. That's why it becomes NH4 plus. So if you look at this, NH3 is acting as a base. NH4 plus is considered as conjugate acid. If you think about reverse reaction, NH4 plus would give off its H plus to OH minus. So it's going to act as an acid in a reverse reaction. So NH3 is the base, NH4 plus is this conjugate acid. So how they're different? They're different in having or not having H plus. Similarly, H2O in this particular reaction, for the forward reaction, is acting as an acid because it donates its H plus or gives up its H plus to NH3, and that's why it changes into OH minus. So H2O is an acid and OH minus would be conjugate base in a reverse reaction, because in a reverse reaction OH minus is going to grab H plus from NH4 plus. Since it accepts H plus, that's why it's a base. So again, here the difference is having or not having H plus. Like water has H plus, making it H2O. OH minus lost that H plus. That's why it's a conjugate base. So keep something in mind here. So I already mentioned this to you. A strong acid readily gives up H plus, and a strong base readily accepts H plus, according to Bronsted-Lowry definition. Now here, with simple analogy, I'm trying to explain to you a strong acid, strong base, and what kind of properties they would have, and the conjugate base would have. If you think about a strong acid, they would readily give up H plus. So I'm showing you here old furniture. So these are all old furniture, and that's like H plus. So a strong acid will be like you have lots of money and you don't want old furniture, so you give up your H plus or old furniture. And that's the case with a strong acid. When you lose your old furniture, that's you are a conjugate base now. And the question is, would you like to hold on to your old furniture? Answer is no. So what that means is, a strong acid would have a weak conjugate base, because when they give up H plus, they wouldn't like to get it back, because a base would like to absorb H plus. So in this case, what we learned here is, if you have a strong acid, you'd have a weak conjugate base, because conjugate base would not like to hold on to its H plus. In this slide, you're looking at list of different acids and their conjugate bases. The top ones are strong acids like HCl. So its conjugate base is Cl minus, which would be a weak one, and as I explained that to you. So as you go down, like for example, this HCO3 minus or H2CO3, for example, is a weak acid. It's carbonic acid. So it's a weak acid, so its conjugate base would be stronger. So it just goes that way. That means a strong acid would have a weak conjugate base, weak acid would have a strong conjugate base. A strong conjugate base means it would like to hold on to its H plus, or reluctant to give up H plus. So that's what you learn from here. Now we're going to discuss the third definition of an acid or a base, which is Lewis's definition. According to this definition, an acid is a substance that accepts a pair of electrons, and a base is a substance that donates a pair of electrons. So if you look at this molecule, NH3, which has a pair of electrons on nitrogen. On the other hand, boron on the accepting end doesn't have 8 electrons, so it would like to get 8 electrons. So the pair of electrons from nitrogen donates to boron. So nitrogen is the donor of electron pair. So that's acting as a base. So a base is a substance that donates a pair of electrons. Now, I have now given all these definitions of acids and bases based on different definitions. But in Chem 112, we'd be mostly dealing with water solution, and we'd be mostly using Arrhenius's definition of acids and bases. So at the bottom, I'm showing you again, just to remind you, when you have a strong acid like HCl, if I have 0.1 molar, it would break down 100%. So at equilibrium, there'd be no HCl left in the form of H and Cl together, and 100% of them would be in the form of H plus and Cl minus separated. So you think it this way, if I have one molecule of HCl, that one molecule would all break down into one molecule of H plus and one molecule of Cl minus. Here, we're showing you in these two beakers that H plus and Cl minus, they got all separated in case of a strong acid. So Cl minus, they're colored different, so you can realize that. H plus is the smaller ion, and those are shown here. So in this water solution, as I said, they'd be all separated. They're not going to be together. On the other hand, on the right side, you're looking at a weak acid, weak organic acid. And that broke down into, in this case, H plus and the conjugate base part. And you can see only a few of them broke down because it's not a strong acid. Now, how do I know which ones are strong acids? Just remember those HCl, HBr, HI. So these are few strong acids, and mostly you have weak acids. So anything other than those strong acids would be weak acids. Almost all organic acids are weak acids. So this is one of them. And here you can see that only few of them broke down and the rest of these remain intact in the solution. And that's the case with weak acids. Now here we are showing you what happens in case of a strong base. Calcium hydroxide, if you start with 0.1, it would break down 100% because this is group 1A and 2A hydroxides. So there'll be no leftover of calcium hydroxide. And then you get 0.10 of calcium ion and 2 times, which is 0.20 of OH minus. Now why 2 times more? Because again, this is the relationship. 1 of CaOH, when it breaks down, gives you 1 mole of Ca2 plus and 2 moles of OH minus. So basically, the number of mole of CaOH breaks down would be 2 times number of ions of OH minus is going to form. And that's why you got 0.20. Now we are going to discuss about autoionization and ion product of water. This is another equilibrium constant expression. In water, you'd not expect 100% of water remaining as H2O. Rather, you'd have H3O plus and OH minus. A small part of water molecules would give reaction like this. So if I write down equilibrium expression, H3O plus on the top, OH minus on the top, and H2O, but since there are two H2O, they'll be squared. So, I mean, that's how you're going to set up. And then doing some math here, you can see that multiplying both sides by H2O squared, and then you get Kw, which is given by H3O plus times OH minus. Now H3O plus is often written down as H plus, so we just simply write down as H plus. So H plus, when it's in water, it makes H3O plus. So we are going to write down this expression as Kw equals to H plus times OH minus in water solution. You can apply it in any water solution at 25 degrees centigrade, and that value is known. This is called water dissociation energy, constant, or ion product constant of water. Now when pH is equal to 7 at 25 degrees centigrade, it's a neutral solution. It's greater than 7 is basic, less than 7 is acidic. Now pH is defined as log of inverse of H plus, and POH is minus log of OH minus, or log of inverse of OH minus. And also I'm reminding you, Kw is H plus times OH minus equals to 10 to the negative 14. And then by taking minus log on each side, you get minus log of Kw, which is pKw, is given by pH plus POH, and that equals to 14. In solving a number of problems, you're going to use this. In this slide, we're showing you some of the common solutions and what kind of acidic or basic pH they have. Like gastric juice is quite a bit acidic compared to lemon juice, as you can see here. And the value of H plus is shown on the left hand side, which is 1 times 10 to the negative 1 molar in gastric juice, but the lemon juice is 10 to the negative 2. And So as you go down, you'd see that how that acidic property changes, and it's interesting to see this. And also milk, you can see here, this is the value for milk. It's almost neutral. So rainwater is slightly acidic, and coffee, black coffee, is also some acidic property. On the other hand, in lime water has basic property. I'm not talking about the lemon juice. This is just the water and lime added there. Milk of magnesia, that's also basic. And so it's interesting to know these. Among the weak acids, as I mentioned, that these are mostly organic acids. Citric acid, acetic acid are well known. Citric acid, you get it from lemon juice. Acetic acid, vinegar has acetic acid. Now, at this point, you don't have to know those formulas, but you need to know the characteristics of weak acids or weak bases. In a weak acid, I already mentioned in just a few minutes ago that weak acids would not break down 100%. Partly it would break down. Say maybe out of 100, maybe 2-3 molecules would break down. So that's something you need to keep in mind. Weak bases give this reaction that we're seeing at the bottom. React with H2O, where hydrogen goes to nitrogen with pair of electron, and OH gets separated here. So it breaks down. So that's the typical basic reaction. And weak bases would be like ammonia or derivatives of ammonia, where nitrogen has a pair of electrons. Now here you're seeing a number of acids, and they're depending upon how many acidic hydrogens they have. Like in most cases, you have more than one acidic hydrogen. That's why we have Ka1 and Ka2. So for acid dissociation constant, we use Ka, A for acid. Now, carbonic acids, we're quite familiar with carbonic acid. That's why I'm picking this particular one. It has two acidic hydrogens. Let me show you. H2CO3. In first step, it will break down as H plus and HCO3 minus. In second step, HCO3 minus would break down into H plus and CO3 2 minus. So from this table, I see Ka1, that means first time when it breaks down, is more acidic because it's a lot easier to break down for the first time. 4.3 times 10 to the negative 7. Second time, we call it Ka2 when the second hydrogen gets out. 5.6 times 10 to the negative 11, much smaller. Remember, larger value of K value means greater concentration of product. Here product is H plus. So in first step you get a lot more H plus than in second step. Now it's quite understandable because in second time you're removing H plus. Already there is a doubly charged, negative charge CO3 2 minus, which is trying to prevent it or hold on to H plus. So it's much harder. In the first step, you're removing H plus from just a singly negative charged HCO3 minus. So this is much easier to separate.